I'm going to go to Desmos. That's the website that I gave you guys in Insight. So let's just graph 4x minus x squared. And I'm going to graph the tangent line, negative 6x plus 25. And I just want to see if this looks correct. And you can see here, here's the point 5, negative 5, and it does indeed look like this is the tangent line to my parabola. You can see right here the tangent line, and let me try to zoom out for you. And there we have it. There's the tangent line. There's the parabola. Okay. So there's another way to express the derivative with slightly different notation, and sometimes it makes computations easier. So I'm going to show you that. So the first one that we saw was the derivative of f at a, in other words f prime of a, is equal to the limit as x approaches a So this is the definition we had on the first page. And remember, it's just the slope of the tangent line. So one thing I can do is, I'm going to draw a very similar picture. Here's A. Here's where x was. Now instead of using x and a, I'm gonna think of x as a plus h, where h represents the distance between a and x, which could be on either side. Then this becomes f of a plus h. So this point is a f of a. And all I'm going to do now is use this just use this to write the slope of the secant line instead of using x. So I get the limit as, so let's start with the rise. The rise is going to be f of a plus h minus f of a over a plus h minus a, that's the run. And now the limit as x approaches a, we can say this in terms of h. We could just say h approaches 0. Now doing a little bit of simplification, I get that this is equal to, now a plus h minus a is just h. So this is yet another way that I can express the slope of the tangent line, or in other words, our derivative. So next I want to do one example using that definition. Here it is. So in this case, a is equal to 3. I'm going to compute g of a is 3 over 2 times 3 minus 1, so that's 3/5. Okay, so my slope of the tangent line, in other words, g prime of 3, or the derivative of g at 3, is equal to, let's see, g of 3 plus h minus g of 3 over h. Now filling these in, I have g of 3 plus h is just 3 plus h over 2 times 3 plus h minus 1 minus g of 3, which we found to be 3/5, all divided by h. So next I'm going to simplify. And this I could just write as 5 plus 2h, right? So this is 5 plus 2h. And the next thing I want to do is I want to clear out all these fractions. If I were to take the limit now of any of these expressions, I'm going to get the limit is 0 over 0. That always happens with the derivative. So over here, in order to clear out these two fractions, I'm going to multiply the numerator and denominator by 5 times 5 plus 2h. So this will be multiplied by this. And this gives me, this times this gives me 5 times 3 plus h minus, in all over, don't forget to multiply this by this, I have 5 times h times 5 plus 2h. Simplifying gives notice how I leave this in factored form. Sorry, this should be a negative 6h. Okay, once again, I'm still going to get 0 over 0 as my limit, but that's fine because I have this common factor here of h. Now, this is a rational function. If I use direct substitution, I have that the limit is equal to, sorry, this should be a negative 1. The limit is negative 1 over 25. So this is the slope of the tangent line at when x is equal to 3. Okay, there's one last thing I want to talk about. And these are just some more examples, some quick examples that might help with the homework. So here I have an example. If f of 7 is equal to 9 and f prime of 7 is equal to negative 3, what is the equation of the tangent line to f at x equals 7? Well, we know that f passes through the point 7, 9. And this is also a point on the tangent line. So first we get a point. We're also given that f prime of 7 is negative 3. That's the slope of the tangent line when x is 7. Now I have a point and a slope for the tangent line, so I can use point-slope form once again. And the equation I get is y minus 9 is equal to negative 3 times x minus 7. And this is the equation for my tangent line. Okay. Another type of question you might see in the homework is this type. each limit represents the derivative of some function f at some number a. State f and a. The first thing you want to do is, think about which formulation of the derivative are you looking at. With the h approaching 0 and the h here, this looks like the second formulation of the derivative I showed you. Okay, it looks like this one. And it appears to me that in this case, a is 16. Okay, so I'm going to kind of guess a is 16. And if a is 16, then it looks like my function f is the fourth root function. Now, just to double check, I'm going to check and see if this is f of a. So, f of 16 in this case is the fourth root of 16, which is 2. So I'm pretty happy with these choices. Next, I'll look at this example. Now this one doesn't have the h in the bottom. In fact, it doesn't even have an h or an x or anything. There's t. But this looks like it has the structure of a slope. So this to me looks like x approaches a. And the only difference here is that the variable x has been, instead they're using a t here. Which is fine. You can always, give things different names. Here to me it looks like my function f would be sine. And when I look at the comparison here, it looks like a could be equal to pi over 2. So I see the a here and the a here, just as you see it here and here. And just to double check, I'm going to see if this is actually f of pi over 2. So this is going to be sine of pi over 2, which we know is 1. So that checks out. The last thing I want to mention is you'll see some examples that involve rates. So rates are what you get anytime you compare two quantities using a quotient, okay, like a over b. So sometimes we'll be working with a function, s of t, that represents position, displacement, or height. So the idea is that you have something moving in one direction. It might go back, it might go forward, but it's like a particle or a car or something moving. And we want to measure the position after time t. Okay, so one thing I just want to help you with these homework problems, recall from section 2.1 that if this is a position, if s is a position function, then the average velocity between two different points in time is just given by this expression. And this corresponded to the slope of a secant line. It's just the rise over the run, change in s over the change in t. Now the new thing here that we can compute is the instantaneous velocity. So this is the velocity at a moment in time. This is given by the derivative of the equation of motion, or the position function. So just take the derivative at t if you're ever asked to find the velocity. It's that simple. You're really just being asked for the velocity. Finally, the speed. We don't think of direction when it comes to speed, so we take the absolute value of the velocity, and that's what the speed is. Okay, so if you're looking for the average velocity, you're just going to do some algebra here. If you're looking for the instantaneous velocity at time t, you're going to find the derivative at time t using either of those two formulations we talked about. And if you're looking for the speed, you're just going to find the absolute value. You'll see these problems come up with, position of a particle, a ball is thrown up and you're looking at the height, you have a height function. Just anytime you have an equation of these equations of motion.